Hello everyone, I am Ankit Mondal and this is my ELL 101 project, Analog to Digital Converters. We will see how op-amps help us to sense this world. Now, why do we need analog to digital converters? The physical world is full of quantities that are varying continuously. That is their analog in form. But the digital electronics we use are binary in form. They use digital input, which is discrete. So something needs to convert these inputs. For example, when we use the internet, the radio waves are in the form of analog signals. It needs to be converted into ones and zeros for the computer to work on it. It is for this reason that we need analog to digital converters. And so let us first understand how analog and digital signals are represented. An analog signal, briefly put, is a continuous signal which can take any value within its range. The digital signal, on the other hand, can only take a handful of values. Usually, it can take only two values, and these are usually called the on and off states. In a binary paradigm, the number is represented in the form of ones and zeros. So 14 would be represented as 1, 1, 1, 0, as it is 8 plus 4 plus 2. So an analog to digital converter should take the analog input value at any point of time and convert it to the corresponding binary value. Let us look at how this process is done. First, if say the input is 14.8 volt, then the op amp needs to compare the value and give the output as 14. Then this 14 needs to be converted into the binary form, that is 1, 1, 1, 0. We will now see how these two parts are handled. We will study the 2-bit analog to digital converter and we will study the flash converter model. First, let us understand how an op amp is used as a comparator. If the input to the non-inverting input is greater than the input to the inverting input, then the output will be high, and in the other case, the output will be low. Let us now look at the LM339 comparator, which is a simple circuit containing the comparator. In this circuit, the V reference, that is the input to the non-inverting terminal, is fixed at V by 2, and the input in the inverting terminal is varied. If V in is greater than V reference, then the output will be very small. So the current will flow down the resistor and out. So the op amp and the comparator will be on. On the other hand, if the input voltage is less than the reference voltage, then the output here will be quite high and will almost be equal to V. And so current will not flow down through this resistor, and so the op amp will be in off state. Now that we have learned the working of the LM339 comparator, we will see how this can be used to take the input and give the greatest integer value. For example, in the 2-bit converter, the range is up to 0 to 4. So in the 4 volt, we use 4 resistors to evenly divide the voltage. These are supplied to the reference values at the non-inverting terminals. Now, if the input voltage is greater than the non-inverting terminal, then as we have seen earlier, then the comparator will be on. So here, if the V input is between 3 and 4, U3, U2 and U1 all will be on. If it is between 2 and 3, only U2 and U1 will be on. If it is between 1 and 2, only U1 will be on. And if it is between 0 and 1, none of the op amps will be on. Now coming to the remaining part, that is the encoder part. We have got the greatest integer value, because if the input is 3.2 volt, then only then all of U3, U2 and U1 will be on, and so D3 will be on. So we have got the 3 volt output. Now the 2-bit encoder should take this 3 volt output and convert it into the 1, 1, that is in 3 in binary form. How does it do this? Well, it has logic gates. First, it uses the XOR gate, 3 XOR gates, and the first terminal of the first gate is grounded. The second terminal is connected to A3. For the second XOR gate, the connection is made as shown, and the last one is also connected as shown. So when A3 is on, the voltage is between 3 and 4 volts. Only the first logic gate will be on. Only the first logic gate will be on, and so only the first 2 diodes will be on. The current will flow down through both the branches, and so both Q1 and Q0 will be 1. If A3 is off and A2 and A1 are on, then only the second logic gate will be on. So current will only flow through the second gate, and only Q1 will be on, resulting in 1, 0, that is 2. Similarly, if all A3 and A2 are off and only A1 is on, then current will only flow through the last diode, and only Q0 will be 1. So the output will be 0, 1. If none of the inputs are on, the output will be 0, 0. Now that we have seen the working of the comparator and the encoder as a whole, we will see how the internal mechanism of this logic gates are. That is, we will see how these logic gates can be built with diode and transistors. The XOR gate can be built with the help of NAND gates as shown. The logic table shown over here gives you an idea of how this is same as the XOR gate. The NAND gate is built using an AND gate followed by a NOT gate. The AND gate is in fact realized with the help of two transistors operating in the saturation region. So when both A and B are high, then both the switches are on and current flows down this branch. So the output is 1. In all other cases, the output will no current will flow down the branch, and so the output will be 0. So this in fact works as an AND gate. In the NOT gate, if the input A is high, then the transistor will be on and current will flow down this branch. So the output over here will be low. On the other hand, if the input here is low, then no current will flow through the transistor and the output will in fact be high, that is equal to VCC. Thus, this will act as a NOT gate. So we have seen how the AND and NOT gates can be used to build the encoders and how the op amps can be used to compare the values. Thus, we have seen how building up from the simple devices that we have learned in our course, we can build a device such as the analog to digital converter, which is such an important part of our daily lives. It is used in telecommunications, signal detection, and many more areas. Thank you. These are the references which I have used.